Hi everybody, this is Dr. Nigro with our screencast on elastic collisions. Make sure that you have reviewed the screencast covering recoil and inelastic collisions as well. All right, so we need to define an elastic collision so that we can recognize it in comparison to recoil or inelastic. All right, so we're still going to stick with our two objects, but this could be more than two. But an elastic collision occurs when two objects that are traveling separately collide. All right, now that traveling separately, remember, maybe one object's moving and the other isn't. Both objects are moving towards each other, or maybe both objects are moving the same direction where one is chasing the other. All right, but they're traveling separately. They collide and bounce off of one another. All right, now the word bounce here it's more for a visual. All right, they don't bounce necessarily, depends on what the object is. All right, but they bounce off one another and continue moving separately. All right, and this is the important part, this move separately. All right, if you remember, an inelastic collision is defined as two objects that interact and then move together after the collision. So an elastic collision varies in that the two objects bounce off each other and continue to move separately afterwards. All right, so a great example of an elastic collision, I love them, but bumper boats. If you live near us, you can go to Kimball's and ride those. All right, but when they come into contact, they just bounce off one of each other. They're still colliding, all right, but they bump, bounce, elastic collision. All right, now just like we saw with recoil and inelastic, all right, momentum is conserved during these collisions. Okay? All right, so when investigating this type of collision, it's again important to draw a diagram before and after so we can see what's going on. All right, the direction of travel is important. We're going to use arrows to show that, and we can use the sign of the velocity value or words in the description of the collision to determine which way those carts are moving. Remember, left is going to be negative, right is going to be positive when it comes to our velocity values. All right, so let's look at situation number one. All right, we have two carts, cart A and B, and they're sitting on a frictionless track. Each cart has 1 kilogram of mass, and cart A is moving with a velocity of 2 meters per second to the right, while cart B is at rest. Cart A collides with cart B elastically, so it tells us the type of collision. And cart B has a final velocity of 2 meters per second to the right, and cart A has a final velocity of 0. All right, so the question is, was momentum conserved in this collision? So let's start with our diagram. So before, we have cart A, and it is moving to the right at 2 meters per second. Up in front of it is cart B, and according to the problem, it is at rest, so it's not moving. After the collision, cart A has 0 velocity, so it is no longer moving, but cart B is now moving out in front at 2 meters per second. Oh, it needs wheels. There we go. All right, so this is a diagram of our before and after for this situation. All right, now to prove whether momentum was conserved or not, we have to calculate our momentums before for cart A and B, and then after for cart A and B. All right, so let's start with cart A before. We have 1 kilogram of mass, and it's moving at 2 meters per second to the right. So the momentum is its mass times its velocity. So that's going to be 1 kilogram times 2 meters per second, which equals 2 kilograms times a meter per second. All right, so 2 kilograms times meters per second. All right, now we look at cart B. We have 1 kilogram of mass, and it's at rest, so 0 velocity. So the momentum of B before is its mass times velocity, which is going to be 1 kilogram times 0. So we get a momentum value of 0 here. All right, so that's before. Now we move to after. All right, again, cart A has 1 kilogram of mass, but it has a final velocity of 0. So the momentum of cart A is going to be 1 kilogram times 0. So it's going to have a momentum of 0 after the collision. Cart B has 1 kilogram of mass and is moving to the right at 2 meters per second. So the momentum of cart B, its mass times velocity, is going to be equal to 1 kilogram times 2 meters per second, or a momentum value of 2 kilograms meters per second. All right, so we've got our momentum values for each cart before and each cart after. And now we're going to check and see if momentum is conserved by filling in our momentum values and seeing if the two sides equal each other. All right, so cart A before was 2 kilograms times a meter per second. Cart B was 0. Cart A after was 0, and cart B was 2 kilograms times meters per second. So if we look, 2 plus 0 is 2. On the other side, 0 plus 2 is 2. So the before equals the after. So yes. So was momentum conserved? Absolutely. Remember, the momentum before equaled the momentum after, which is the definition of conservation of momentum. All right, now let's look at a different type of problem. All right, in this situation, we still have our two carts. They're both on their frictionless track. They each have a mass of 1 kilogram. Cart A is moving with a velocity of 4 meters per second to the right, and cart B is moving at 1 meter per second, but also to the right. Cart A collides with cart B elastically, and cart B has a final velocity of 2 meters per second to the right. What is the final velocity of cart A? So this is a little bit different. Here we are going to assume that momentum is conserved, and we're going to use that equality to then solve for an unknown. All right, but first we're going to start, as we always do, with our diagrams. So here's cart A moving at 4 meters per second to the right, and somewhere out in front of it is cart B, and it's moving at 1 meter per second, but also to the right. Okay, we have cart A after the collision. Now, I don't really know which way it's going because I don't know that final velocity value. So again, I'm going to come back and fix my diagram when I'm finished. Now, I do know that cart B is moving to the right at 2 meters per second. So that I do know. All right, so here's what I have. Now we're going to do our calculations. For cart A before, 1 kilogram of mass, a velocity of 4 meters per second to the right. So the momentum of A is going to be equal to 1 kilogram times 4 meters per second, and we get a momentum value of 4 kilograms times a meter per second. So 4 times a meter per second. All right, we then look at B. So cart B has a mass of 1 kilogram, and it is moving, is it 1 meter per second to the right. So our momentum for B is its mass times velocity, so 1 kilogram times 1 meter per second. And we get a momentum of 1 kilogram times meters per second. So 1 kg times a meter per second. Now note both of these momentum values are positive because everybody's moving to the right. All right, now we're going to look at the momentum after. All right, so for cart A, I know its mass, 1 kilogram, but I do not know its velocity. That is our unknown. All right, so if I wanted to solve for the momentum, which is mass times velocity, I would end up with 1 kilogram times my unknown, the velocity of A. And that's as far as I could go. 1 kg times the velocity of A. All right, I do know more information about cart B though. So I know that it's got a mass of 1 kilogram, and I know that it was moving now at 2 meters per second to the right. So the momentum of B, its mass times velocity, is equal to 1 kilogram times 2 meters per second. All right, so we end up with 2 kilograms times a meter per second for that momentum value. All right, now I'm making an assumption here that momentum is conserved, and you can make that assumption as well. All right, we're going to fill in before and after. So for cart A before, it had a momentum of 4 kilograms times a meter per second, and cart B, 1 kilogram per meter per second. For cart A after, I have my mass value, and then I have my unknown. And then for cart B, I have 2 kilograms times a meter per second. All right, so if I add the before, I end up with 5 kilograms times a meter per second, equal to 1 kilogram times my unknown, VA, plus 2 kilograms times a meter per second. All right, now I'm trying to isolate this velocity value. All right, so the first thing I need to do is move my 2 kilograms times meters per second to the other side. And right now it's added, so I need to subtract it from both sides. We'll just do the opposite. This becomes 0. And then over here, I'm going to have negative 2 kilograms meters per second. All right, and so when I take 5 and subtract 2 from it, I have 3 kilograms times a meter per second left. And that's going to be equal to 1 kilogram times my velocity value. All right, divide both sides by 1 so that this goes away. And I'm left with 3. Oops, I left my unit off. That's a big no-no. You guys know that. All right, the unit here is going to be meters per second, and that's the velocity of A after the collision. All right, so if I go back up to my diagram, I can erase my left arrow because it's not moving to the left, and I can put in 3 meters per second. All right, now if you look, because the two carts have the same mass, you'll see that the velocity values on one side, 4 plus 1 is 5, are equal to the velocity values on the other side. That's kind of nifty how that works. Okay, so that's just another way to utilize this idea of conservation of momentum by finding an unknown velocity. Okay?